Okay, HVAC 1 design class. Recorded lectures, 2 lectures for the other class, and I didn't want you guys to feel like I was ignoring you, didn't care about you. So here we go. So this will be this lecture and probably another video or two will make up for the first class that we'll miss next Tuesday. And then I will send you another email later with similar information for next Thursday's class. And then, of course, you know you have homework to be working on the unit selection as well as the HAP modeling of a residential dwelling. Okay, so we talked about package units last time, and I think it was last time. And so the idea, especially if it's a DX package unit, it basically has everything inside this box. And all we have to do, so that means the refrigeration cycle, and if it uses natural gas, it has a little furnace in there. It can combust the natural gas and produce warm air to go directly into the space. So we set this thing, if it's on the roof, we set it on a roof curb typically that looks like this. We hook up our supply and return ducts. They can come in the bottom, or if it sits on the ground outside, they can generally be configured to come in and out one of the sides or the end, however the manufacturer has designed the unit. Hook up power and natural gas if necessary, and we're good to go. Got everything we need right there. Put a thermostat someplace appropriate and hook in the control wires, and we're ready to be warm in the winter and cool in the summer. So then we talked about the split system, which also is, we usually think about as a DX type unit most of the time. Again, there's exceptions to everything just about, but by and large, the split has the condensing unit sitting outside that has the compressor, the condensing coil, and maybe some refrigerant receivers and stuff like that, but basically, and a fan. There's a fan suspended in here that pulls air across the coil and blows it up the top. It takes away the heat of compression as well as the heat from the space and dumps it to the air outside. The indoor unit has the evaporator coil. If it's natural gas, it has a furnace section. It may have filtration involved. Here we're showing a power air cleaner. This shows a humidifier. So for the winter time when spaces want to dry out because it's the ambient air outside is so dry, the moisture wants to dissipate from inside to outside. We have a hard time maintaining moisture levels. So if you purchase a humidifier, we run a little water in there and it will inject water. It will probably have a little heat source to make steam and inject that into the supply air in order to maintain moisture levels during cold, dry weather. So that's a possibility. Okay. Now let's see, we're gonna have to go around in a circle a couple times here. Get this thing back where we want it. So this figure is kind of a traditional air handling, a central air system. You could call that an air handling unit, and we're also showing a return fan and some ductwork on it. We're going to have a heating coil and a cooling coil here. The heating coil is most likely hot water. You can have steam, usually one of the others. This type of system typically does not combust natural gas. So we would have some external equipment to either produce a boiler to produce steam or a hot water boiler to produce hot water that would get pumped through the heating coil. And then we have a cooling coil as well. So what we're showing here, here's a supply fan that's blowing through the coils. And you see what happens. This is set up to provide cold air that goes across the cooling coil. And see, we have a we have dampers here that control the mixing of this hot and cold air under the control of a thermostat. So they say thermostat controlled dampers. So let's say if it's in the summertime, basically what's going to happen is these dampers are probably going to be almost all the way closed, and we're going to force most of the air across the cooling coil, which makes it cold, and then it mixes with anything to temper it a little bit if we need to do that under the control of the thermostat, and then it goes off to the space to keep it comfortable. This is if we energize both the heating and cooling coils at the same time and they mix air, that is a form of reheat, which would be fairly expensive in terms of operating cost. Tennessee Tech has some systems like this, and sometimes in the summer, you just don't run the heating, don't allow the hot water to go to the heating coil. Go ahead and run the chill water, and if there's any mixing here, this would just be return air that's mixed with ventilation air, and you could temper this a little bit. You don't get as good control, but you don't do reheat, because when you run the cooling coil, you really don't run the heating coil, and when you run the heating coil, you really don't run the cooling coil. So that's an operational modification. It's not the way the systems are designed, but nonetheless, there's still some that operate out there in that fashion. Then we show a humidifier, potential to blow some steam, or it could be atomized water. It's probably steam in here to control moisture levels. And there would be a humidistat someplace tied in with the thermostat to control how much moisture is dumped in here. Returned air from the space comes back. If this has a lot of duct work and a lot of pressure drop, we may actually have to have a return fan to get it back. Smaller systems can most of the time get by on just the supply fan, and the suction on this fan is enough to draw the air back to the unit. It just depends. When you go through the ductwork design, it becomes obvious if you can't do it all with just the supply fan. So if we had a return fan, it would be sucking air out of the space. This would be on the suction side, blowing it back. We show here, we have an exhaust damper, or if we're talking in terms of an economizer cycle, this could be called a relief damper to relieve pressure in the space. Either way, it allows some of this return air to be vented to the outside under the control of this damper. So if this damper is wide open, then this damper would be shut or mostly shut, meaning we want to expel this air, and we're probably in economizer mode. If we're not in economizer mode, we would probably not want to expel too much air, maybe a little bit for pressurization on the space. We would return a lot here, and then we would bring in our outside air for ventilation purposes under control of this damper, which of course all these dampers are tied together and coordinated by the control system. And so we're showing a preheat coil when it's really, really cold outside. Sometimes you really don't want to bring in 0 or -5 degree air even into this unit for freeze potential. So it's a good idea to preheat this stuff up to some nominal 50, 60 degrees at least, so it could then mix, be filtered, and then go across the main heating coil down here. Let's see. About all that comes to mind. This is a blow-through configuration on the fan, because the discharge of the fan blows air through the coil. Sometimes you'll see the fan on the other side, which is called a draw-through, where it basically sucks the air through the coil and then blows it out to the system. Okay, that's about enough on that one. Okay, so this shows a multi-zone system, and this is the type of system we have in Clement Hall, and there's multiple other buildings on campus that have these. The older units are typically constant volume so that the fan blows essentially the same amount of air, the same volume of air all the time. Excuse me. Um, so what happens is we have coils in the unit that are positioned thusly so that some of the air goes across a cooling coil and some goes across the heating coil. So for example, the cooling coil here would be most likely fed by this bottom section of ducts, or this bottom portion of duct all the way across here would have the potential to blow out cold air while the hot air would be up here. And the ducts strap on the front of this and they would encompass both uh, some hot air and cold air capabilities. And so, you know, you could put 3, 4, 5, 6 ducts that go to different spaces, and they would bolt on a section here, a section here, a section here, a section here. And then these little posts that stick up, they control the dampers. So if they rotate one way, you get all hot air. And if they rotate the other, and that closes off the cold air. If they rotate the other way, it's vice versa. You would get all cold air and close off the hot air. And then the thermostat would position the controller so that we get the right temperature of air to keep the space comfortable. So, you know, you can have big spaces and little space. A little space might just have a small duct that straps right on here that just covers up these first 2 dampers. On the other side, you might have a big auditorium. It might take up the other half of this thing with one duct. And then you could get cold air out of here and hot air out of here. And so you would just link all of those with mechanical linkages and have one actuator turning those posts all in unison to control the amount of hot and cold air that goes out to the space. Filter section is back here. You see the fan, the motor for the fan. It's belt driven. The fan is in here. There's the motor, and then the ducts strap on the back side. You have an outside air duct and return air duct. And there they are. So we're not showing the motor here, but you see the heating coil up here with a cutaway and the cooling coil. And notice the cooling coil is much bigger and thicker. The thickness is for dehumidification, and it just takes a bigger, more denser coil to accomplish the cooling than it does the heating. So in this case, this may be return air in the backside and outside air coming in here. They mix, and we're showing filters now laid kind of at 45 or at an angle in here to pull this air across the filtration. Goes through the fan, it gets mixed up pretty well. Gets blown in here where it either is going to go across the cooling coil this way or the heating coil this way and then be mixed out there on the front of the unit. So that's what we call a multi-zone unit. Blow through, coils, fan, filters, mixing box. And that's, I guess those are old figures provided by the train company. We're going to have just some miscellaneous equipment. This would be a large centrifugal fan. So the air coming into this is bolted in right here. If we had inlet guide vanes, they would be set up right there to impart a pre-swirl to the air to adjust capacity on the fan. If we have discharge dampers, they would probably be in the discharge duct up here to just close off against the blast of the fan. This is called the cutoff up here. The fan wheel is in here. It spins around. Usually we've got pulleys attached to the motor that turn this thing. And so the air comes in here and comes out perpendicular to it in this fashion. And these things can come in and blast up, or they can blast different directions. I could blast down. This would be a vane axial fan. So we see this one shows the motor outside of the airflow. So your duct would just be a round duct and it would just bolt right on here. So, and then the other side of the duct going on down bolts on here. And this little portion of fan also comprises a section of ductwork. And so the fan. You see a belt going through here, so it's spinning the fan, and it simply pushes air along in the axial direction. These don't have to be smaller, but I think for HVAC applications, these tend to be smaller fans. The centrifugals can be quite large. This shows a mechanical draft cooling tower. It is induced draft, where it has a propeller fan here in the center. These are I want to call these basins, but I don't think that's the right term. I'm struggling for the term, but they're like a trough up here on top. And so this is where the condenser water from the chiller typically goes. You'd have a pipe hooking in here, dumping about half of it over here, and another pipe going over here, where it would fill up this trough, and then the pressure, the head above that, forces that water down through all these little holes that distribute it out, and it falls down to the fill, which these days is plastic material, just to increase the surface area and enhance the heat transfer. Happens the same on both sides. And then there's a basin down here. The water falls through to the basin. It's cooled while it falls through the tower. This propeller fan is blasting up out of the center of the tower, and it's drawing air in through these louvers. They kind of bring it in at an angle, kind of point it downward, and it kind of turns horizontal and then comes out, turns upward, and blows up out of the top of the tower. So I think we said in class the other day, the standard numbers for an HVAC cooling tower, at least the old time numbers, were 95 degrees in, 85 degrees out at a 77-degree ambient wet bulb. That would be the design condition, the design wet bulb. And that the tower would be big enough to be able to do that for the heat load that was going to be put on it, the chiller capacity, plus the compressor power on the chiller, plus any stray heat transfer that would get into that condenser water would need to be rejected by this cooling tower. Also have typically up here toward the top, there's some plastic kind of wafer type things that the air passes through. They're called drift eliminators to try to keep from blowing any water droplets out of the tower. The tower functions primarily by evaporation. So we evaporate, I don't know, 1% or 1 to 2% of the water falling through here evaporates, and it cools the rest of the flow. Cheap way to reject heat from your building. Okay. This is a picture of a large centrifugal water chiller, again from Train. And I think we've looked at a video that showed this. You have two heat exchangers up here. One is the evaporator, and the other is the condenser. And the refrigerant, this is probably the condenser down here. This would be the evaporator over here. You can tell on the unit because the evaporator is cold. That's where the cooling effect occurs. It's operating someplace in the low 40s, and it'll sweat like the dickens if it's not insulated. So all of the chill water and the evaporator lines will be insulated, and the condenser not so. They're not typically, because the temperature of those things is up in the 80 to 90 degrees, maybe upper 70s, and so you don't have any condensation to worry about, and so you don't typically insulate those. Centrifugal compressor up here, control module, electrical panel, bringing the power in, distributing it out to the unit. We'll probably have some videos that talk about more details on this, but that's kind of what they look like. And they're pretty good size. They can be really large. They can be much taller than a person. Smaller one, maybe not, 100 tons. The smallest centrifugal chiller, don't know exactly. I'm guessing someplace between 50 and 60 tons, probably. You don't see a lot of them. The smaller ones sometimes are for process use in industry. I would say typically 70 to 80 tons and up are what you see conditioning buildings. Much below that, it's probably going to be just what we call DX type equipment. What is this? This is an air-cooled condensing unit. So it's like for a split system, this would compress and condense refrigerant that could be sent out to evaporators located remotely in a facility. They can make these things large. And you see, there's no cooling tower, when you see all these fans up on the top, that's to pull ambient air in through these coils on the side, on three sides of this. And then that's what carries the heat away, and the fans blast up the top to move that air across to provide the cooling necessary for the condenser to work. These are reciprocating compressors. They show 4 in here, so they could be staged on one at a time. So you might have 25, 50, 75, or 100% capacity. So that's the way that can work. Let's see, moving on. Okay, we have some other types of equipment, just so you have some kind of an idea of what's out there in the world. This is a unit that could go above a drop ceiling, or it could look like a unitary, like a unit ventilator in our classroom. These are typically smaller, but they sit in the space or certainly right adjacent to the space where they can blow the conditioned air, this mixed air, directly into the space. So there's no fan. Hospitals are known to have these sometimes. But an induction unit doesn't have a fan. So how it functions is it has primary air, which is typically your ventilation air. It could have some mixed air in it, but it's probably going to be just the ventilation air. And it is provided by a central air handler back in a mechanical equipment room. And so it brings in that outside air and conditions it at least to a point of being neutral. Probably goes ahead and conditions it, to maybe 50, 55, 58 degrees, something like that. And the fan produces a pretty good amount of pressure to move that in here. And then that pressure forces it up through nozzles that are located in this induction unit. And so the air shoots out of these nozzles at fairly high velocity. And that high velocity causes a low pressure region around this. And basically it pulls air up through here, which then reduces the pressure down here. And that induces room air as return air, kind of like, to flow across this secondary coil. And there could probably a filter up here or down here, which is not shown. But this is a secondary coil that provides some additional cooling on this return air. It mixes with the primary air up here and shoots out into the space. So, an advantage of this is that you don't have the noise for a fan. Now you got to be careful that these nozzles are, sized properly, and they're not going to cause a lot of noise, but I think typically they don't. So you don't have to maintain a fan for each patient room on several floors of the hospital. There could be 25, 30, 50 or more patient rooms. Each one have an induction unit and then a central outside air unit that provides this primary air that shoots up, that induces the room air across this secondary cooling. It could be a heating coil if it's cold. You could circulate either hot or cold water through that. And there is a condensate drip pan in the bottom of this, because in the summertime, you put some fairly cool water through this, some chill water, then you can get moisture condensing condenser on the outside of the coil. So that's kind of what an induction unit is. This would be a typical fan coil unit. It is like the unit ventilator in our classroom. The only real distinction that I'm aware of between them is the unit ventilators are just typically physically larger with more capacity. Fan coils tend to be smaller. It's pretty close to the same piece of equipment. And so let's see. So what do we have here? So let's see, the return air comes in the bottom at 7. So this is 7 here. So it's like the unit vent. Let's see, and then let's see where we show on the filter on this thing. Filter 3, yeah, then we got a filter laying in the bottom of this. So the return air comes in here, goes across the filter. These are called, it's a double shafted motor with scrolls on it. These are just circular and they have little vanes and they spin around and they blow the air up through the cooling coil or heating coil. This unit typically only has one coil in it. You can get them with 2 coils. This one is showing one. Sorry about that on the telephone there. We'll get rid of that. Sorry, getting me all discombobulated here. So then the air comes in the bottom, goes across the filter, is by the squirrel cage fan blown up through the coil and then exits into the space. So pretty simple device. All righty. And you can get these that stand vertical, or you can get them that lay horizontal that could be above a drop ceiling. And so you can duct return air into them and have it blow out to a supply air duct. The fans are not terribly strong, so you can't put just a whole lot of ductwork on it. The fan won't be able to move the desired airflow through. Okay. This is the unit vent, which is what we do have in the classroom. Very similar to the fan coil. They're showing 2 coils in here, a heating coil and a cooling coil, which we have in the units in Brown Hall. They don't run water through them at the same time. They're not supposed to anyway, unless the coils are leaking through. Like we talked about, the unit vents over in Bruner. You can look out the window, you see there's a grill on the wall that allows outside air to be pulled in and mixed down here with some return air and then go across the coils and be blown out to the space. You don't have to, you can have a unit vent without this feature. In Brown Hall, like we said, the ventilation air comes from the 100% outside air unit downstairs and comes in those louvers up on that side wall, the interior wall in the classroom, and just gets blown out there. So there's different ways to do these things. Let's see, what do we have here? We're going to rotate. There we go. This is a large package system. And so you see, we have kind of the condensing unit section that we had before on the large rooftop condensing section. But now we have fans, we have return fans and supply fans. This could be a power relief fan when you go on economizer. It can take the air from the building and just blow it out the back of the unit. And so this is the whole kit and caboodle. And these things can get pretty large. I think you can get these up to 200 tons. In my experience, you don't see them very often that large. Certainly 20, 30, 40 tons or maybe 50 tons are really common. And yeah, they certainly make them on up and in larger sizes. Have the controls built into it. There can be furnace sections here if we're going to combust natural gas. It could be a heat pump unit where we utilize the same coil and have reversing valves on the refrigerant flow. But that's the large package, commercial package rooftop unit. Okay, let's see. I'll rotate on around here. Clockwise, there we go. Well, this just shows a room air conditioner like you could buy at Lowe's that you can hang in the window. And so the condenser coil is the part that hangs out the back. It blows the heat and the heat of compression and the heat from the space out the back of the unit. This shows outdoor air. I think most of them probably don't really supply outdoor air. I think you can probably buy it if you want to. Be a little concerned that you don't recirculate this hot air back in here. I take it back. That's not for ventilation purposes. I'm sorry, I misconstrued that. That's the air that's going to blow across the condenser. Yeah, you're going to pull it in over here. It's going to help to cool the compressor and the motor here on the fans, and then blow across the condenser coil. Yeah, so you have to have this outside air. I'm sorry, I misspoke there for a second. Apologies. And then on the other side, so again, we have a double shafted motor. So it's spinning, it's turning both this fan and a blower that will suck the return air on this side. There's a baffle that partitions off the two sides of the unit. This is our evaporator, our cold coil. Got a filter in front, and it simply pulls room air, cools it down, and blows it back into the space. Got some pretty unsophisticated controls, and that's pretty much what the window air conditioner does. Okay, I think I'm going to stop here. I don't want these videos to get too long, and so I'll be posting another one shortly, and we'll pick up here and discuss the operation not only of a single heat pump, but a heat pump loop. Very good. Hope you guys have a good rest of your day.